Okay, so on this slide, what have we done? We've done sensors, right? Everybody okay on sensors? We talked about potentiometers. We talked about absolute encoders, which some of y'all missed on the test, absolute and incremental. Incremental it just gives us a series of pulses that have to be counted. Absolute actually gives us the position, right? So there's an encoder on the conveyor belt, but it's not used in the PLC program. In fact, it's not in any of the diagrams. Talked about limit switches, talked about our non-contacts, right? Proximity switches, we okay? Everybody okay there? Any problems?
I guess on the test that I haven't identified who would be, the furthest light, the one for the furthest distance.
Well, this is pretty good right here in this slide. And these slides are up there now, by the way. But I think what was happening was on the test, it actually gave y'all, instead of using these pictures, it actually gave you. So if we have a transmitter and receiver on each side, it's what? It's through the beam. If it's got a reflector on one side, it's a retroreflective. If it don't have a reflector and it don't have a transmitter on the other side, then it's diffused, right? Hall effect, everybody okay there? And of course on our diagrams they use the same symbol, so a Hall effect and a reed uses the same symbol. It's just a Hall effect will have 3 wires and the reed will have what? 2. I talked about inductive and capacitive, everybody okay there? I looked at ultrasonics. Talked a little bit about pressure. I need to bring I've been playing around with my Arduino. So temperature. So we have different devices that select temperature. We haven't talked about this yet. So we have what we refer to as a thermistor. These are solid state. And this be externally powered. They're what they're called thermistors. So what do you think they do? Change their what? Change their resistance to temperature. Most of these, I got some here. So we have negative temperature coefficients, which means their resistance decrease with temperature rise, which is what we have. And we have what we call positive temperature coefficient, or PTCs, which increase their resistance with temperature. The ones we have are NTCs. Now, the biggest disadvantage is the very first statement up there. What does that say? What does that mean? Yeah, it goes in a curve. So when we look, yeah, it's not proportional. So if you measured it and you measure 150 ohms, that's going to be a temperature. But if you say, okay, this is 80, and then you went up to 200 and you measure it up here, then you say, okay, between 100 and 200, at 150 it should be half of that, but it's not going to be because it's nonlinear. So the curve kind of looks like this, so it angles like this, if I can get that right. So if temperature goes up, and this would be for an NTC, and then this right here is R. So as temperature goes up, then R would do what? Will go down. This would be, it's at a slope. So normally what they do with a thermistor is they'll give you different ohms at different degrees. Now if you knew that, then you can compensate for the slope, especially with a computer. Normally what we do, though, is we use these over a narrow range. So if I use these over a narrow range, then we're looking at a slope that is almost linear, right? You understand that? So these are used a lot in houses. So if you've got a digital thermometer in your house or a thermostat in your house, I guarantee you it uses a thermistor. But your range, when I took physics, I think I might have told my other class, when I took physics, expansion of metals. So we had a steam generator, and then we'd put the metal inside a tube that was sealed up on both ends, and the metal had a gasket it would come out of, and then we put a micrometer on the end, and one of them was up against solid, and when the metal expanded, it would cause the micrometer to move. And we found out right off the bat that different metals have different coefficients of expansion. So if I take two metals that have different coefficients of expansion and I bond them together, literally bond them together, then what's going to happen when we heat it? Yeah, they're going to expand differently, which is going to cause it to do what? It's going to cause it to bend. Thank goodness. This is one of the primary ways circuit breakers work. We run the current through a bimetallic strip that's got a little bit of resistance. As current goes up, it heats up. When it gets to a certain temperature, it trips your breaker, right? You understand that? A lot of your old thermometers, thermostats, use bimetallics. But they put it in a coil, and it was a bimetallic strip, but it was just coiled into a spring. And then, of course, what would happen? Well, when it cooled down, it would cause the spring to contract. It would cause it to spread out. It would cause this tip up here to move, and then we'd come up here, and they had a mercury switch up here that we used one side for heat and the other side for cold. And when it cold, it would contract and it would go into more of a helix, right? You understand that? And when it tilted over, it would cause my heater to turn on. On the other side was air conditioner, right? You ever seen these old thermostats? I got one over there in the other class. So I don't know why I did that. Bimetallic strips are very, very popular to sense temperature, especially when we're just trying to sense when something gets up to a certain temperature. They're pretty dang accurate, and since they change their shape, it's pretty easy to have them set in with some type of plateau that's got a spring hold in them, right? You understand it? And as soon as it warps, what happens? It snaps open. And so that's why if you're standing by a circuit breaker when it snaps or pops, what do you have to do? You can't reset it instantly. You got to wait for that bimetallic strip to do what? To cool off. Well, we can use these in thermal switches all over the place. And they're pretty accurate too, so they'll trip at a certain temperature. But when it cools down, it will do what? It'll automatically do what? Reset. So we use these in small horsepower motors as the overloads, where they'll put it in series with the stator on the motor. And if the motor tries to pull too much current over time, it takes a little time. That's why your circuit breakers, when they pop, you've had an overload, right? You understand? They don't pop when the overload occurs, but it had an overload. So I need to add bimetallic strips to this because they're very, very popular. RDTs, and then of course what's popular now is infrared. So used to, when they would come into these vents right here and they wanted to see if they was working, they would do what? They'd climb up on a big old ladder, and they had basically a meat thermometer they would stick up there, and then they'd have to sit there and wait for either the bimetallic strip. A lot of thermometers, by the way, use bimetallic strips. They'll put the strip in a helical under there, and it either comes out or goes in, right? You understand that? So a lot of meat thermometers use diamond tap strips to measure temperature. But infrared, what we do here is we have an infrared sensor, and then we do what? Of course, this is an electronic circuit, and what does it do? Measures wavelength and then calculates what? Temperature. So these guys are not very cheap. But now you got the guy coming here, instead of climbing up there and measuring it, he'll get his little infrared thing and point it up there and measures the temperature. Now the big problem we have is it's affected by what? Well, other bodies do, and temperature and other bodies. So, if you don't have those things lined up perfectly at what you're doing, so a lot of them have a laser sight on there. It's not using the laser sight, but it's using it to make sure you're pointing that thing at exactly what you want to measure temperature. Yeah, I imagine. I don't know. Harbor Freight's good. I buy stuff from Harbor Freight. But I don't buy important stuff from Harbor Freight. I don't buy meters from Harbor Freight. I buy my welding wire from them, my rosin welding wire from them. It's real cheap there. Stuff like that. So these are temperature that we use to measure temperature. Of course, temperature is very, very important, right? Because when things get hot, it usually means something's not right. Okay, so last thing we'll look at here, and then we'll try to get into a lot more lab when we come back, is so this. Have you ever anything I know about electrical motors? Not necessarily. It might be electromagnets. So we have two categories. What's the two categories of electric motors? What's that? The two main categories. DC and AC. So we have DC motors and AC motors. Huh? So tell me everything I know. Y'all have had motor controls, and we covered it, most of the stuff in motor controls. Well, they both have electricity, so it's hard to say. We have AC motors, and then they're subdivided into two categories of what? Single phase and three phase. And then, of course, single phase motors are used for low horsepower, low torque, right? They're very inefficient. And we have three phase, which are used for high horsepower, high torque, and they're very efficient, right? DC motors, what type of DC motors do we have? Stepper, which is toward the end. We want the basic DC motor. Those are the types of DC motors. How we call shunt, separate excited, series, compound, right? So we have shunt, series, compound. We have separately excited, which I need to make sure I put up here. We have stepper motors and we have brushless motors. Over on the single phase, we have passive start motors, we have passive run motors, we have split phase motors, and shaded phase motors. Three phase, we have Y, we have delta, we have Y delta, and Y round, and then we have synchronous. There's no such thing as a synchronous DC. Even though the brushless might be sort of that. So these are DC motors. We've got two fields. We have one that's stationary that's called the field. And then we have one that rotates that we call the armature. The stationary field can either be an electromagnet or it can be a permanent magnet. Very okay. So all the motors on our lines over here are permanent magnet motors. So when we say it's a permanent magnet motor, we mean that the field is permanent magnet. Now, a lot of people call them the rotor and the stator. Most people understand what you're talking about, but technically those are not correct. But I've heard people all over the place call the rotating part the rotor and the stationary part, the stationary field, the stator. Now those terms are the terms we use for AC motors. Technically, the rotating part of a DC motor is called the armature, and the stationary part of the DC motor is called the field. The stator is a term we use for AC motors, right? You understand that? So what do? Well, to make a motor move, we always have two fields, two magnetic fields. And what we got to do is we got to make one of them move. You understand that? One of them's got to move. Now, DC and AC, we have motion. Right, you understand that? AC, we have motion. DC, we don't have motion. So if I've got a 12-volt DC motor, I put 12 volts on that. How do we cause one of the fields to move? We let the motor cause it to move, right? You understand? So what we have on the back of it is we have this unit called a commutator, which is made up of different slots. When it turns, it causes these, here comes the power, so we have to have what we call a commutator, and we have to have what we call brushes. So what happens is that I put DC on the brushes connect to the commutator, the commutator connects to a bunch of coils of wire, which makes a electromagnet. Now what's the advantage of an electromagnet over a permanent magnet? You can turn it off and on, and you can control its strength, right? So the more current we put through those coils, the more the magnetic field is stronger. The less current we put through the coils, the magnetic field is weaker. Everybody understand that? Another thing we can do is we can turn the field off and on. So we can turn these motors off or on or off, right? We can cause them to stop or we can cause them to run just by taking away a field. But this commutator is set up on different segments, and this is not exactly right. The brushes are actually they're away from the fields. They're 90 degrees out from the fields. So what happens, I put current through there. It creates a north and a south. One of these are a north and a south, and it causes it to pull. Right? You understand? And then once it's in motion, it wants to do what? Stay in motion. Well, then what happens, as soon as it gets where it's going to try to lock in, what happens? Well, the brushes switch the field. Not the field, switches the current in the armature, which constantly causes this to be north, this to be south. This is north and south over here, which would cause the motor to run in this direction right here, right? You understand? If I change the direction of the current in the armature, then the direction of the motor is going to change. Or we could change the direction of the field, which we don't normally do. A permanent magnet motor is definitely, we're going to change the direction by changing the voltage that we apply to the armature. So the field, the stationary magnet field, the stationary magnetic field can either be electropermanent magnet, sometimes referred to as the what? Stator. It's not technically correct, but if it was my boss saying it, calling it stator, I'd say okay. But if it's one of you calling it stator, I'm going to say no, it's the what? Armature. The armature is the rotating magnetic field. It's always what? An electromagnet. So the armature is always an electromagnet. Sometimes referred to as the what?
Rotor.
So what's the commutator? A slotted copper ring used to transfer a current from the source to the armature. The slotted magnet mechanically changes the direction of current in the armature, causing the motor to do what? Rotate. So the motor itself creates that field that's in motion, right? You'll understand that. Brushes, these are carbon blocks with copper wires attached used to transfer current from the power source to the commutator. Normally reversed by what? Changing the voltage on the armature. Y'all understand that? Huh? And there's several reasons why, because shunt motors and separately excited motors and compound motors, if the field opens when the motor's running, the motor can run away. If the field to the armature opens, the motor will stop. So it's safer to do it with the armature, even though a series motor won't make any difference because you can't open up the field without opening up the armature. But what we need to understand is that we come up with a standard way. If we got a standard way, we always reverse DC motors the same way, by reversing the what? Armature. So here's a shunt motor. This is what we call a separately excited motor. So typically used in industrial speed applications, a common source or this common source has good speed relations over varying lengths. It's got a pretty good starting point. Separately excited, what can we do with it separately excited? If I change the armature voltage, it's going to change the speed. If I change the field voltage, it's going to change the torque. But if torque goes up, speed goes down, which is kind of strange. So if I increase the strength of the field, the speed goes down. If I decrease the strength of the field, the speed goes up. And this is why if you open that sucker up, if there's any residual magnetism in there at all, which there's going to be, then these motors right here will run away on them. They won't start, but they could run away, right? Understand? Because as the field goes down, as the torque goes down, speed does what? Goes up. So between the two, we can have a really, really good controllable motor. If I increase the field, if I increase the speed, I get more torque. I increase the voltage on the armature, I can compensate for speed. So what's nice about a separately excited motor is we can control both the torque and the speed. We had them on the motors that the take-up reels on number 4 galvanizing line. They constantly had to change their torque because the spools kept getting bigger and bigger, but they didn't want the speed to change. So what they would do is they'd vary the field, but then they would vary the armature in the opposite direction to make them suckers always run at what? The same speed, even though the torque of the motor was varying. So you don't want to be spooling. So if that sucker's running at 700 feet a minute, then you want your take-up reels to run at 700 feet a minute. Well, what happens when the spool gets bigger? Well, the spool gets bigger, the torque changes, right? It takes more torque to turn it, but you want it to run at the same speed. So they use these separately excited motors up there. So most of the DC motors out of US Steel were separately excited because they were just more easier to control. Permanent magnet motors, these are a form of shunt motors. The field's in parallel, but we don't put any. These have speed change with armature current, good speed characteristics, good starting torque, very low horsepower application. We run off with this. What type of motors are in your car? Except the starter. The starter is a series motor. But every other motor in your car is a what? Permanent magnet motor. On your windshield wipers, on your fans, everything is usually permanent magnet. Series motor. These guys are neat. Great starting and run torque, very poor speed regulation. Also called a universal motor. These guys here will run on AC or DC. Of course, you have to be real careful with the frequency, so that's why they call it universal motor. So if you change the connection, the voltage connections on the armature, I remember doing that in motor controls. So if we change both the field and change the armature, what happened to the motor? Ran in the same direction. So normally what we do to change it is we change the armature because we usually don't want to fool around with disconnecting and connecting the fields, right? Does that make sense? But a series motor, if you change the direction, you're changing both the armature and the series, and the motor will run in the same direction, which is pretty neat. So these guys are called universal motors because over a range, over a frequency range, you can run these things on AC or DC. Of course, one of the biggest disadvantages is they got a commutator, just like a DC motor, and so they have commutators and they have brushes. So what does this mean as far as maintenance goes? You have to maintain those brushes. Those brushes wear out over time, right? And then, of course, you got to keep that commutator clean. But these guys here have very, very poor speed regulation, but they have really, really good torque and run torque. We use these in vacuum cleaners. This is what your starter on your car is. It's a series motor. Hand drills use series motors. You ever see it spark in the back? And you can really tell those. You can hold them up in your hand and they run real, real fast. As soon as you put them down into a board or something, what do? They slow down, but their torque goes what? Goes way up. Yeah. Yeah. You get a good old. I got a half-inch Craftsman. Got that handle on the side. Yeah, you better be careful with that thing. Compound motors. What's the advantage of compound motors? Yeah, high starting torque, good speed regulation. We have different ones. We have what we call a cumulative compound. One of them they wire it in the same direction as the shunt. The other ones they reverse it. Series field aids the shunt. So these have high starting torque, but less speed regulation. And differential has a lower starting torque, but really, really good speed regulation. So these are what most motors are out here still. If you got DC motors, they use a compound motor. And we'll do this too. We'll set up a lab on this. One of the most popular ways. So what we can do to control the speed of a DC motor? What do we usually do? We change the voltage on one. So if voltage goes down, speed goes down. If voltage goes up, speed goes up. Now it's DC. So I can come up here and I can control the speed with a rheostat. But what's the problem with this? Okay. called SCRs. Very popular. The problem with SCRs is that once you turn them suckers on, the only way you can turn them off is to take the current away. So they work real great on AC because AC reverses polarity 120 times a second, right? So you turn them on, and then they'll conduct the rest of the cycle. So I might be putting this into my pulsating DC,